So the purpose of the immune system is to fight things. It's to fight bacteria and viruses and other things that you don't want in your body. So that's what it does. And a question we can ask is, how does the immune system know not to attack your own body? And that might seem like a strange question or an obvious question, but it's actually not obvious, the answer to it. And so in this video, we're going to go into why it's not obvious and then how the body actually does prevent its immune system from attacking itself. So another way of saying this is, how does the body distinguish self versus non-self? And by that we mean, how does it tell the difference between your own body, your own proteins, your own cells, and foreign proteins or cells or things that shouldn't be in your body? So how does it know to attack these and not to attack these? So to find out why the question itself is not obvious, let's go back to B cells and talk about B cells. So here we have a B cell, and here's its nucleus with some DNA. And the most important part of the B cell that we care most about is its B cell receptor, which later, if it becomes active, can be released as an antibody. Now this B cell receptor is what's going to bind to foreign pieces of foreign bacteria or viruses, and these antibodies are going to bind to those things and help your body get rid of them. And the important thing to remember about B cells is that these antibodies or these B cell receptors are coded in the DNA of the B cell, but that they're different for every B cell. So every B cell has a unique set of antibodies and B cell receptors that it makes. And so we'll give them slightly different colors to make that obvious. Here's one with slightly different DNA and a slightly different B cell receptor. And the really critical point to remember is that these B cell receptors that will become antibodies are generated at random. So your body kind of shuffles the DNA here and creates a unique B cell receptor and antibody for each B cell. And it's precisely that fact, which is that they're created at random, which means that your body is in danger of creating B cell receptors and antibodies that can react to your own body. Because while this guy might be good, while he might react to, let's say, a bacteria out here that you want to get rid of, so while that's good, this guy might easily create a B cell receptor and later an antibody that can react to something you don't want it to react to. So for example, let's say this is an important protein in your body, maybe it's insulin. You would not want a B cell to be created which will react to insulin, because then maybe it'll start creating antibodies that bind all the insulin in your blood. And if you don't know what insulin does, don't worry about it, but by binding to insulin, it'll prevent insulin from doing its function, which is very important. So how can you keep your body from making B cells that would react to yourself? In fact, there's no way to do it, because, as I said, this process of creating different B cell receptors and antibodies is totally random. So there's no way to keep your body from making B cell receptors or B cells that will react to yourself. So what does that mean? That means that you're going to make them, but you need to find a way to figure out which ones are reacting to you and to get rid of them. So you need to figure out a way to kill the ones you don't want. And by the way, we're talking about B cells here, B cells, but everything we're saying is equally applicable to T cells. So let me draw one here. T cells, it's equally applicable because T cells also have a T cell receptor that's generated at random, and you only want that T cell receptor to react to foreign things, to non-self things, and not to self things. So the processes we're going to talk about are equally true, maybe even in some cases more so true for T cells than B cells. So let's go to the bone marrow to figure out how this process works. And we're going to the bone marrow because that's where B cells come from. It's where they get their unique antibody or B cell receptor. They get that by changing their DNA a tiny little bit, by shuffling pieces around. And so let's look at a couple of these B cells, which are still young. They haven't yet been allowed out of the bone marrow. They haven't been vetted to see if they should be allowed out. And each one has its unique receptor. So let's draw a few of those receptors here. And let's say that one of these guys reacts to self. So one of them reacts to some protein in your own body that you don't want it to. And again, that just happened at random because you're creating these receptors really at random. So let's say that the guy that we're going to want to get rid of is this one, because he reacts to, let's say it's insulin again, like up there. Really, we should have drawn insulin in yellow to show that it goes with this receptor. So let's say this guy reacts to insulin. So how can you figure out that this guy reacts to self? And the answer is actually quite simple. The answer is that you just need to keep around the various proteins that your body uses. You need to keep them around in the bone marrow while these B cells are being vetted. And so for example, here you'll have a little insulin, a very small amount, but it'll be there. You'll have a little bit of, some other protein, let's say maybe hemoglobin. You'll have some other protein here. You'll have yet another protein over here. And so all these proteins will be around. And so what your body does at this stage in development is it says, whatever B cell binds to something, with its B cell receptor in the bone marrow will be killed. And so this B cell right here that recognizes this insulin protein, the fact that it recognizes it means that it'll bind, and that'll cause a little bit of a chemical change in the B cell or something, and one thing will lead to another, and the whole system will be programmed so that as a result, this guy will die. So every B cell that recognizes self, if it sees that self molecule in the bone marrow, it will be killed. And this works because your bone marrow will have most of the abundant proteins in your body. They'll be present there so that you can make sure that you weed out all the B cells that react to self. Now what happens after this step is that these guys who have been vetted, they can proceed onwards to maybe a lymph node, somewhere where they can begin to actually be active, now that they've sort of gone through basic training here in the bone marrow. And you might ask yourself, well, what about here? What about here when one of these B cells that doesn't react to self, what about when it interacts with a bacteria that you actually want it to fight? Is the same thing going to happen? Is it going to die just because it recognizes the molecule that it's made to bind to? And the answer is obviously not. You don't want this guy to die because you need him, because you want to fight this bacteria. And so the reason why he doesn't die is because, well, we're in a different environment. There are different rules, there are different other cells around, and this B cell has matured and become different. So the rules are different, and he's not going to die. So this weeding out of B cells that react to self proteins is sort of the first of two mechanisms that I'd like to talk about that the body uses to not react to self. And actually the same exact thing happens for T cells, except it doesn't happen in the bone marrow. It happens in the thymus because that's where T cells mature. So in the thymus we have really the identical process where T cells differentiate, and each one has a unique receptor, and the ones that react to self in the thymus too strongly are killed. But it's not a foolproof method, or else we wouldn't need step 2. Every once in a while a B cell will get out there. A B cell will escape which reacts to self. And it's just because every process has its mistakes, and maybe you don't have every single protein here in the bone marrow in enough abundance to find the B cells that react to a protein of your own body. So let's say this is a B cell that escaped the bone marrow even though it reacts to self. What's going to happen now? Well, it's going to find that protein that it was sort of made at random to react with. And so it's going to find that protein that your body makes and that your body needs, and it's going to bind to it. What's it going to do now? Well, if you remember, it's now going to take that protein, ingest it, break it up into little pieces, and then present it on an MHC2 molecule. An MHC2 molecule. And if you recall, it'll just present a small piece of that protein on the MHC2 molecule. Maybe it'll present a different piece of the protein on a different MHC2 molecule over here, something like that. And the reason it does this is because it needs a T cell to come along. So here's a T cell. And it needs a T cell to come along that will recognize that same piece that it's put there on its surface. And it needs that in order to activate. So it's going to sit there and wait for this T cell to come along who has the perfect receptor. And so here's that T cell. And they're going to interact, and they're going to have some kind of intracellular kiss that's going to finally allow this B cell to activate. So usually without the T cell coming, and recognizing the antigen that the B cell reacts to, the B cell cannot activate. It needs this T cell to recognize it. And so this is exactly the second mechanism of defense that I'd like to bring to your attention, which is that even if a B cell escapes that reacts to self, almost always it's also going to need a T cell that reacts to self to come and activate it. And so you need both the B cell to escape the weeding out in the bone marrow and the T cell to escape the weeding out in the thymus for you to get an active B cell that's now going to start putting out antibodies that react to self. And by the way, this cellular kiss here is usually going on in the lymph node. Now, looking at this whole process, you might have a few complaints, and I encourage you to think about how it might go wrong. Well, one way you might think it could go wrong is, what if bacteria got into the bone marrow? And certainly that's very, very possible, because when you get infections, the thing that's infecting you can move around your body. So if this bacterium gets into your bone marrow, does that mean that now this B cell is going to bind to it and therefore is going to be killed? Because at this stage, whenever the B cells bind to something, they're killed? And the answer is yes, this is exactly what happens. But the reason why it's not too much of a problem is that even if you have this bacterium here in the bone marrow for a week or two, or maybe a month, after that, once this bacterium goes away or is killed, then it won't be there anymore, and you can start producing these B cells that react to that bacterium again. And hopefully you already had a bunch of these B cells that could react to this bacterium that you had made previously and that were already out in the lymph nodes. And so those guys will be there to fight the infection, while maybe the infection might be in your bone marrow, preventing you from making more of those B cells to kill it. So you already have some of those B cells out there in the lymph nodes, and they can proliferate out there and sort of lead the battle from there. Now, even though your body has these mechanisms to keep your immune system from reacting to yourself, it still happens sometimes. The process still goes wrong sometimes, and the result is autoimmune disease. And it's called autoimmune because you're immune to yourself, and so your immune system basically starts attacking your own body, and some pretty terrible diseases can result. And so to kind of bring it to life for you, I'd like to tell you about one example of this. So this is a muscle fiber, and the way your muscle fibers are activated, because you don't want to be flexing all of your muscles all the time, the way that they're activated is that they have a little receptor, which I'll draw here. And this receptor is ready to receive little molecules from a neuron, part of a nerve. It receives little molecules from this neuron that activate this receptor and therefore activate the muscle fiber. And so if you want to tighten this muscle fiber, you just need to send a signal down the neuron, and it'll release these little molecules which will activate the muscle fiber. But in one example of autoimmune disease, you get antibodies against this receptor here on the muscle. And so they bind to it, and that either stops it from functioning, makes it impossible for it to react to the neuron's signals, or causes that receptor to be destroyed. And those are two mechanisms that have been seen. And so in this autoimmune disease, what do you think will happen? Well, what happens is that your body can no longer activate muscle fibers as easily. And the disease is called myasthenia gravis. And the etymology of that is that my sort of means muscle, and asthenia means weakness. So muscle weakness, and gravis just means it's serious, because it gets serious over time. If you can't activate the muscle fibers in your body, you slowly become paralyzed. So you don't need to remember this exact mechanism. That's not really important, but I just wanted to give an example of one kind of autoimmune disease and how it works.